This video is on derivatives of natural log. So for the derivative of the natural log of x, remember this means log base e. The derivative with respect to x, d dx of natural log of x is equal to, and this comes out to 1 over x. Remember, the derivatives are really based off of the limit of the difference quotient. We're showing it here without proof. Just making sure that you have an understanding of what the rule is. So for the natural base, right, natural log of x, the derivative is 1 over x. And, it's a pretty straightforward rule. We'll do a couple examples with it, and then we'll talk about variations of it if the argument of the log was a function. So, for example, if I said to differentiate, and remember that means take the derivative. Let's take a look at just y equals 5 ln x, right, or natural log of x. Remember, when I write ln x, it's natural log of x. It's a function. And when I want to take the derivative here, well, we have y prime is equal to, now 5 ln x means a constant 5 times a function. When you have the derivative of a constant times a function, the derivative, or the constant just stays in front, and then you just take the derivative of here, natural log of x, which is 1 over x, and then 5 times 1 over x, simplifying this, is just 5 over x. So we have y prime equals 5 over x, and that would be the derivative of 5 ln x. Looking at another one, if I said y equals 1/3 ln x, again, don't let this fraction throw you off, right? It's a constant times a function here, so when I take the derivative, the constant will just stay in front, is 1/3, and then multiply by the derivative of the function. The derivative of natural log of x, according to our rule, is 1 over x. And so then this will equal to, remember how you multiply fractions, straight across the numerator, 1 times 1 is 1, straight across the denominator, 3 times x. So y prime here equals 1 over 3x. Pretty straightforward problems, right? Constant times a function, the constant stays in front. Let's take a look here at something a little more complex, not too bad. If I said we had y equals x cubed natural log of x plus 4x squared. So keep in mind all of our derivative rules. When I look at this, I have y equals x cubed ln x. This is a function times a function, so you can't just take the derivative of each piece of this. Remember, you would have to actually use, if you have a function times a function, the product rule for this. And then the derivative of this other term, you can just take the derivative term by term. So here we've got y prime equals product rule on this first part. Remember how product rule works. The derivative of the first function, so derivative of x cubed would be 3x squared, times you leave the second alone, so times ln x, plus it's the derivative of the second function. Well, the derivative of ln x is just 1 over x, times the first, so times x cubed. That's the product rule. And then now we have to take the derivative of the 4x squared. So that'll just be plus derivative of 4x squared, bringing the 2 times 4. Using the power rule gives us 8. X to the 2 minus 1 is x to the first power. And now we'll just simplify this. Simplifying here, we end up with y prime equals, we have 3x squared ln x, and you can just leave that as is. You can't multiply into that natural log, remember, because that's its own function, plus 1 over x times x to the third. One of these x's will cancel with one of the x. The x to the third will cancel with the x here to leave me with an x squared. Right, so 1x cancels with 1x, but there's still an x squared left. Plus, we have 8x here. And can I combine any of that? Well, the answer is no, because these are not like terms, so you're going to leave it just like that for our derivative. The key thing, though, is acknowledging that product rule. A lot of times people miss that, and they try to just take the derivative of each piece individually and just put them next to each other. And remember, you can't do that for a product of functions, right? A function times a function, when you take the derivative of it, you have to use the product rule. Now let's take a look at one more here. If I call this one D, let's say I had f of x equals natural log of x over x to the 9th power plus 1. So, taking the derivative of this function, I have a function divided by a function, so you should know that we need to use the quotient rule. If I'm looking for the derivative f prime of x, remember how quotient rule works. Alright, quotient rule says we want the derivative of the numerator, so derivative of the top, derivative of ln of x is 1 over x, times the denominator, so times the bottom, x to the 9th plus 1, minus, make sure you have minus there, the derivative of the denominator, which derivative of x to the 9th is 9x to the 8th, derivative of 1 goes to 0, so just minus 9x to the 8th, times the numerator, so times ln x, alright, over the denominator squared, right, over the bottom squared. Alright, so that's just using our quotient rule. If I said do not simplify, you could leave it like this. If I want you to simplify, which, if I don't say do not simplify, that means I want you to simplify, we're going to simplify this. So let's take a look at what we would have. I'll distribute the 1 over x through here. So I end up with 1 over x times x to the 9th. One of those x's will cancel down to an x to the 8th, right? Because x to the 9th over x gives us x to the 8th. 1 over x times 1 will be plus 1 over x. Minus, this is still 9x to the 8th ln x. And it's over x to the 9th plus 1, the quantity squared. And really, I don't want to leave this as a complex fraction, right? I have a fraction inside of a fraction here. So I'm going to multiply both numerator and denominator to clear fractions by the LCD of all the fractions I see, which is just x. I'm going to multiply this all by x, and I'm going to multiply this by x. This is just to simplify our complex fraction. So distributing x through here, x times x to the 8th would be x to the 9th. X times a 1 over x would be plus 1. Minus x times 9x to the 8th ln x makes this 9x to the 9th ln of x, or natural log of x. And then this is over down here, x times this, just leave it right next to it, x times x to the 9th plus 1 squared. Remember, you can't distribute the x into here because of that power of 2 on the outside. None of these are like terms. Nothing factors out to cancel. You have to leave it like that. So those were, derivative problems that, you've seen before, but now we have a new function that we know the derivatives of, derivative of natural log of x. We're going to talk about the chain rule for natural log. All right, so the chain rule, is when you have a composition of functions, a function inside of a function. So when we talk about the chain rule for natural log, I'm really saying that the argument of the log would be a function. So this is going to be the chain rule for y equals the natural log of f of x. Alright, so we say given y equals natural log of f of x, then y prime, the derivative is equal to, now remember how chain rule works. It says take the derivative of the outside, you keep the inside the same, and then you multiply by the derivative of the inside. The outside function is natural log, the inside function is f of x. So when we took derivative of natural log, when it was just x, it was 1 over x. So this will be derivative of natural log of f of x will be 1 over f of x. That's the derivative of the outside times the derivative of the inside. Well, it's times f prime of x. And this is typically how I'll write it when we see it. And then, this simplifies if you multiply this to f prime of x over f of x. So some people know the rule this way. Understanding that using chain rule, derivative of the outside is 1 over whatever's on the inside times the derivative of the inside. And that would be the rule for natural log. So, having an understanding of that, it really is a chain rule just like you normally would use it. It's just a matter of you know, 1 over x was the derivative of just ln x, so 1 over the inside stays the same as 1 over f of x times the derivative of the inside. Let's take a look at a few examples here. So if I said we had to differentiate, alright, so find the derivative. For the first one we'll look at, I'll say, is y equals natural log of x to the fifth. So now I have a function inside of a function. So I'm using chain rule. The chain rule for log says, right, the derivative of the outside, natural log is the outside function, so it's 1 over, you keep whatever's on the inside the same, so it's 1 over x to the fifth, right, times the derivative of the inside. Well, what's the derivative of x to the fifth? Well, it's 5x to the fourth by the power rule, bringing the 5 down in front, subtracting 1 from the exponent. And then, you know, you could simplify this, right? This is really 5x to the fourth over x to the fifth. If you just multiply those together. And then how does this simplify down? Well, I can cancel 4 of these with 4 of them in the denominator to give me just an x down there. So we have y prime equals, this ends up being 5 over x. Once simplified. Right? So y prime equals 5 over x once you simplify it. If you remember our rules about logs, you might notice this. Right, using our log rules, if I have y equals natural log of x to the fifth, if the argument of the log is just something raised to a power, there's a rule that says you can bring the power down in front. So this is a rewrite step. We're not taking the derivative. We'd end up with y equals 5 natural log of x. And then if I took the derivative of this, y prime is equal to, now it's a constant times a function, it would be 5 times 1 over x, which equals 5 over x. And you notice they are the same. You know, this only works if your argument is something to a power, right? It's just a whole factor to a power. So in this case, you know, this is a way of rewriting it to get there maybe a little quicker, but you don't always want to do that because it won't always work out as nice. And you'll see that in the next example. If I said I had y equals the natural log of x to the fourth plus 3x squared. Okay, so this is the derivative of natural log of a function. So it's a chain rule, right? It's a function inside of a function. And when I look at this for y prime, remember derivative of the outside is derivative of natural log is always 1 over whatever was on the inside. So 1 over the inside stays the same, so x to the fourth plus 3x squared. Make sure you leave the inside the same, right? So 1 over whatever is on the inside times the derivative of the inside. That's chain rule. Derivative of the inside, x to the fourth, gives us 4x cubed, plus derivative of 3x squared gives us plus 6x. And so if I simplify this, right, I can write this as, you know, y prime equals, if I just wrote this as 1 times this in the numerator, is 4x cubed plus 6x. Over in the denominator, you've got x to the fourth plus 3x squared. And what you should notice now is that if you can factor to simplify, you should, right? So if I can factor something out of both numerator and denominator and cancel, I can do that. What you can't do is start canceling right away. You can't cancel like the 6 with the 3 or these x's with these x's because remember, these are all individual terms. You only can cancel factors from the numerator and denominator that are the same. From the numerator, if I factor out a greatest common factor, I could take a 2x, and that would leave me with, if I take 4x cubed, taking out the 2x gives me a 2x squared, plus 6x factoring out the 2x gives me a plus 3. Over in the denominator, x to the fourth plus 3x squared, I could factor out a factor of x squared times what's left over will be x squared plus 3. Well, what can cancel here? Well, now I can cancel this x with one of these, so there's still one remaining. And, you know, nothing else cancels. You can't cancel these 3's, you can't cancel these x squareds. So you end up with y prime equals, and we've got 2 times 2x squared plus 3 over x times x squared plus 3. Now, if you wanted to, you know, this here, you could distribute the 2 back in and the x back in. It'll give you an equivalent answer. It doesn't change anything. Let's take a look at this one. This one's going to be a little unique. If I said I had f of x equals the natural log of x squared minus 5 over x. Now, you know, I'm going to talk out loud about what you would do, and then I'm talk about how, you know, our properties of logs helps us make this a little easier. If you were to look at this, and you see you have natural log of a function, you'll say you have a function inside of a function, and you would try to use our chain rule for logs. So you would say, you know, 1 over the argument of the inside, so it would be 1 over this fraction in here, times the derivative of the inside, so it would be multiplying by the derivative of the inside of this, you know, is a quotient rule problem, because it's a function divided by a function. So you'd have 1 over this fraction times a quotient rule for all of this. Within that, you might have a chain rule as well. So it gets kind of complicated. So if you ever see this where you have a function that is of log and there's division inside, remember our rule. This is going to be a rewrite step that'll make this derivative a little easier to handle. If you have division inside of the log, you can rewrite it as subtraction of the logs individually. So this would be the natural log of the numerator, natural log of x squared minus 5 minus natural log of x. So I'm not taking a derivative, I'm rewriting it in equivalent form. Our log rules say if we have division inside of a log, I can write it as subtraction of the log of the numerator minus the log of the denominator. Now, why is that helpful? Well, now I don't have to do that whole quotient rule part while I'm approaching this, because now when I go to find f prime of x, right, when I go to find the derivative, I take derivative term by term. The derivative of this first term, natural log of a function, well, you still have to do a chain rule for log. Alright, so natural log of x squared minus 5 is 1 over, you keep whatever is on the inside the same, so it's 1 over x squared minus 5 times the derivative of the inside. The derivative of x squared minus 5 is 2x, so that's a chain rule being used for log on the first part, minus the derivative of natural log of x. Well, derivative of ln x is just 1 over x, so you don't have to do a chain rule on this because the argument is just x. If you did do a chain rule, right, it'd be 1 over the inside times, what's the derivative of x? Well, just times 1. So it gives you the same thing, in case you forgot. And then this leaves us with this here. We end up with 2x times 1 is 2x over x squared minus 5 minus 1 over x. And you can leave it like that. That's f prime of x. A little easier than if you were to go the other way at the beginning. Now, if you did do it the other way at the beginning, you could get to an equivalent answer. You know, if you started right away by using your chain rule, but you would have a quotient rule in there, you would have to simplify complex fractions. There'd be a little bit more to it. So, you know, keeping that in mind as you approach these, if you see a log with division inside of it, you know, you might want to use that, the quotient rule to help us simplify it first, then take the derivative. Let's take a look at an application. So for this example, if I said we had n of a represents the number of units of a product sold, and A represents the amount spent on advertising in thousands of dollars. Alright, so we have n of a, this is a function. Right, so, and that's going to be equal to, say, 1,000 plus 200 natural log of a. And we'll have this condition where a is greater than or equal to 1. Right, so I haven't asked you a question yet, I'm just kind of giving you the premise. So N of A represents the number of units sold when $1,000 are spent on advertising. Right, so when I say A is in thousands of dollars, when I say A is greater than or equal to 1, that means that the minimum that they can spend, right, is $1,000, right? So the lowest amount that they spend is $1,000 on advertising. Just to kind of point that out. So looking at this, we'll ask you a couple questions that go along with it. So first part, how many units are sold when $1,000 should say is spent on advertising. Okay, so how many units are sold when $1,000 is spent on advertising? So basically what they're asking you to do is find, N when A is $1,000. Now remember, don't substitute in 1,000, right? A is in thousands. So if I want to spend $1,000, I'm looking for N of 1. Right? Because 1 is $1,000 when I talk about subbing in for A. So we're looking at the number of units sold. It's going to equal 1,000 plus 200 times natural log of 1. Well, what's the natural log of 1? Remember, log of 1 is always 0, right? It's saying e to what power, right? Natural log is base e. It's saying e to what power gives me 1? Well, e to the 0 power gives me 1. So this is really equal to 1,000 plus 200 times 0, just so you can see it there, which just equals 1,000. Remember, that's going to cancel out. 1,000 what? Well, 1,000, what are we trying to find? How many units sold? So when $1,000 are spent on advertising, 1,000 units are sold. Let's talk about another question. If I said find and interpret n prime of 10. So first off, before you can find n prime of 10, you have to find n prime of a, right? Because you need the derivative before you substitute in. You can't just substitute in 10 and then take the derivative. So we need n prime of a. Let's talk about finding the derivative. We got the function right up here. So the derivative of 1,000, right, we're going to do this term by term. Derivative of 1,000 will just be 0, right, plus the derivative of 200 ln a. It's a constant times a function, so the constant stays in front. What's the derivative of natural log of a? Well, it's 1 over a, right? Derivative of natural log of x would be 1 over x. Derivative of natural log of a is 1 over a. You don't have to use a chain rule here because, the function is just a single variable. If you did, it'd be times 1, which would just give you the same thing. So we know that n prime of a is equal to, this is just going to be 200 over a, right? 0 plus anything is just going to give you whatever this is itself. This is 200 times 1 over a is just 200 over a. So we know that we have n prime of a equals 200 over a. Now that's not what it asked us to find. It asked us to find n prime of 10, but you needed n prime of a before we could do that. So what's n prime of 10? Well, we're just substituting in. So n prime of 10, it's 200 divided by 10. And keep in mind what this 10 means, right? It's 10 what? A is in thousands of dollars. So it's really saying the rate of change, right? That's what n prime is telling us. When $10,000 is spent on advertising, it's the rate of change on the number of units sold. So we have 200 divided by 10, which ends up giving us 20. Right? And what are the units on this? Well, n prime is the units of n. If you want to remember how to find units, right, it's like dn over dA. That's what n prime really means. The change in n over the change in a. So change in n is 200 units sold per What's A? Well, A is thousands of dollars, right? Going back up here, it's thousands of dollars spent in advertising. So it's units sold per $1,000 spent on advertising. So if I was to interpret this, it's positive, so the rate of change is positive, so it's increasing. So we want to say when $10,000, right? That's what this A is. When $10,000 spent on advertising, the number of units sold is increasing by 20 units for every $1,000 spent. Okay, so it's a sentence describing what we found. Increasing because it's positive. Remember, we're talking about the rate of change here. So it's important to know that. And then maybe we'll just do this problem here, just last question, just as a review. If I said how much should be spent on advertising if 3,000 units are to be sold. So if the company wants to spend or wants to sell 3,000 units, how much should they spend on advertising? Well, that's telling us, the 3,000 is telling us that we want this side of the equation, right, the N of A, right, the number sold to be 3,000. So we're going to really solve this for A. So we're going to have, here we would have 3,000 is equal to the 1,000 plus 200 natural log of A. To solve this, we're going to subtract 1,000 from each side, because you want to isolate that log term. So you'd have 2,000 equals 200 natural log of A. And then we'll divide both sides by 200 to isolate the natural log. I'll bring this up here. Which will give us, 2,000 divided by 200 will just give us 10. Equals natural log of A. And, well, how do you solve this log? Well, you really rewrite it as an exponential, right? You can exponentiate. Natural log of A, right, is equal to 10. This is saying natural log is base E, so it's saying e to the 10th power is equal to A, right? So e to the 10th power, the base is E, the power, the exponent is 10, is equal to A. And so now we found it. Now let's approximate this, right? So e to the 10th power is the amount they should be spending. E to the 10th power, thousands of dollars. But let's approximate this. So if we did this on your calculator here, we would have e, so second e to the 10th power. And that would give us 22,026.465. So this A is approximately, we'll say this is 22,026. And remember, this is in thousands of dollars, so I'm going to put the 3 decimals, 0.466. Right, this is thousands of dollars. So 22,026.466 thousands of dollars. To get this just to be in dollars, you would multiply this times 1,000, because in thousands of dollars. So you end up with, what do we got here? You're really moving the decimal 3 over. So if we were here, we would have, looks like 22 million. 1, 2, 3, 4, 5, 6. Yeah, 22 million. 26,465 dollars and 79 cents would be how much they would want to spend on advertising. All right, so make sure you know that the amount was in thousands. So depending on what the company is selling, that would be the amount they should sell. Hopefully this video helped with understanding derivatives of log. The example at the end here is an application of using logs in a business sense.